everybody. I'm Tanya Birch from the Google Earth Outreach team. We're here to kick off lightning round number 2 with an amazing, inspiring group of people. And buckle your seatbelts because we're going to go fast. Every speaker has 5 minutes to talk. And as the 5-minute time approaches and more speakers come in, that's your cue to wrap up your final points. And then I'll introduce the second speaker. So is everybody ready to get started?
Ready.
Ready.
Excellent. Okay. First up, we're welcoming Christian Thomas from Skytruth.
Hi, everyone. My name is Christian Thomas, and I'm a geospatial engineer in Skytruth. Today, I'm going to be talking about the work that my partners and I are doing to monitor and measure reclamation and reforestation on surface coal mines in central Appalachia. Next slide, please. Mountaintop removal mining is an incredibly intrusive and destructive method of resource extraction. Operators first clear-cut native forests before using explosives to remove soil and bedrock, exposing coal seams beneath them. This waste material, called overburden, is then deposited into neighboring valleys in a practice called valley fill. As a result of this practice, over 2,000 miles of streams in the region have been buried. Streams associated with mines have higher rates of erosion and nutrient pollution, both of which contribute to decreases in aquatic biodiversity. These pollutants can also be transferred to terrestrial ecosystems through food webs. And the disturbances caused by mountaintop removal mining also create significant barriers to the recovery of native Appalachian forests. In addition to the environmental impacts, over 40 peer-reviewed studies have linked mountaintop removal mining to negative human health impacts, including increased rates of dementia mortality and increased risks of lung cancer. Next slide, please. This animation shows the expansion of coal mines near Charleston, West Virginia from 1985 to 2015. Mountaintop removal mining is the primary cause of land cover change in central Appalachia, and since 1976, 5,900 square kilometers of land in the region have been directly impacted by mountaintop removal mining. And while production for the region has decreased since 2008, the amount of land disturbed to extract a ton of coal has increased by a factor of 3 since 1985. Next slide, please. After knowing when and where mining is taking place, some of the first questions that arise are if and how the land recovers. This graphic shows the growth and expansion of the Hobart 21 mine in West Virginia from 1985 to 2015. As mining progresses across the site, we can see evidence of reclamation as older portions of the mine, which were bare earth, transition back to vegetation. Reclamation is tied to a bonding process, and mine operators are required to set aside money to be used for restoring the landscape in the event that the operator fails to adequately restore it. As they reach different levels of reclamation, more of their bond money is returned. But if these efforts are inadequate, the burden for any additional reclamation falls on states and local communities. Next slide, please. Building off of our earlier work mapping the extent of these mines in Earth Engine, we're now developing an approach for assessing mine land recovery with the goals of identifying if and where reforestation is happening on former mines. Next slide, please. Exploring how post-mining reforestation compares to pre-mining vegetation and examining the effectiveness of different reforestation approaches. Next slide, please. Using Earth Engine, we aggregate spectral metrics for all mine sites from 1984 onward using Landsat satellite imagery. Once sites are no longer active, they are compared to reference forests that are located in the same EPA Level 4 ecoregion. Next slide, please. By comparing the spectral signatures of former mine sites to those of nearby healthy forests, we can track and measure changes to the site. We identify the efficacy of reforestation, and we're also examining how fully sites recover, as well as what level of consistency there is in defining bond release status, both across state borders and if there are differences by operator. Next slide, please. The data that we're creating will be useful for enforcement authorities by helping them to assess recovery. It will provide transparency for local communities in a very opaque system, and it will also help drive the next generation of scientific research working to truly understand the impacts of mountaintop removal mining. In the second quarter of 2020, coal production for the Central Appalachian region reached an all-time low. And as more and more coal companies file for bankruptcy, state reclamation funds are in danger and may be unable to fully cover the costs of reclaiming the mines. This underlines the importance of effective bonding that protects the public from haphazardly abandoning mining operations that may be unsafe or unusable for other purposes. Next slide, please. Thank you very much for your time. We will be publishing our results and data in the coming months, so keep an eye out. And if you have any questions or would like to get in touch with us, my contact information is available here. Thanks.
Thank you very much, Christian. That was an excellent presentation. Next up, we have Grant Canet from the Smithsonian Institution.
Hi, I'm Grant Canet with Smithsonian's Working Land and Seascapes Initiative, and it's a real pleasure to be able to participate in the Geo for Good Summit. All around the world, ecologists and wildlife biologists like me use spatial models to understand and predict changes in biodiversity due to human land use. This process allows decision makers to understand the likely consequences of their actions and to ideally make decisions that benefit both people and nature. Next slide, please. Coming from an academic background, I'd grown used to working on highly customized spatial analyses that were performed over months or even years that generally wind up being published in academic journals. But in 2015, colleagues at the World Wildlife Fund began an effort to assess mitigation options for a planned road through a massive forested landscape in the country of Myanmar, a place that is still home to tigers, elephants, and many other rare and endangered species. Next slide, please. The goal was to strategically place wildlife crossing structures in key locations along the road in order to reduce wildlife vehicle collisions and minimize the fragmentation of wildlife habitat. The catch was that construction of the road was already underway, and it was a mad dash to map wildlife corridors in time for design modifications to be implemented. These efforts ultimately led to a report and maps like the one here, where blue areas are predicted to see the highest intensity of use by several threatened mammal species. Next slide, please. In theory, the process of mapping wildlife movement corridors is simple. In this example overview, you start with satellite imagery, map important landscape features, assign travel cost values to each feature, representing how likely wildlife are to successfully traverse these areas. And finally, we can calculate the cumulative travel cost to anywhere on the landscape from known wildlife sources. In the upper right map, areas in red are difficult for wildlife to reach and would be expected to have less wildlife movement than the green areas. In practice, however, this process often requires data from multiple data repositories, multiple software programs, and lots of coding and analysis expertise. Next slide, please. While working with Myanmar colleagues on our road crossing assessment, we just had this realization that the way we are accustomed to doing research is simply too slow, too complicated, and required too many spatial data inputs from too many data repositories. To respond to an urgent real-world data need, we basically had to put everything else on hold. Next slide, please. Fortunately, we realized that with Google Earth Engine, we could access or create all of the spatial data inputs we needed, and could execute a number of widely used corridor analysis methods in mere seconds. Working in Myanmar, where downloading a single satellite image used to mean spending a night in the office to take advantage of peak internet speeds, this was a real game changer. Next slide, please. In fact, basic wildlife corridor mapping with Earth Engine turned out to be so easy that WWF and Smithsonian hosted a hackathon-style event with wildlife biologists and government officials to teach these methods. We adopted a no data, no problem philosophy by showing participants how to create spatial data for roads, railways, and land cover directly in the Earth Engine interface. We've since been working to adapt these methods into an Earth Engine application that you see in action on this slide. Next slide, please. We're also working to implement other common analysis workflows in Earth Engine. This example from South America shows the process of taking species location data, relating those locations to environmental conditions, generating habitat suitability predictions using various methods, then merging those predictions using a weighted average based on model performance. Next slide, please. In collaboration with WWF, we're still working on translating additional spatial analysis workflows into Earth Engine. A couple key areas of interest are to be able to link land cover change analysis with the ability to forecast the future state of ecological processes. We're also working on methods to identify optimal road alignments, accounting for various engineering costs and environmental impacts. We're also starting to adapt these Earth Engine workflows for supporting management planning at wildlife conservancies in Kenya, planning around sustainable infrastructure development with Myanmar's Ministry of Construction, and for various upcoming training courses. With that, I'd like to acknowledge that it is a team effort that has gotten us to this point, involving a great group of collaborators at Smithsonian and WWF. Finally, we're interested in thoughts, ideas, or input from the broader community, so feel free to reach out. Thanks for your time.
Thanks so much, Grant, for such an inspiring talk. Let's have a round of applause for Grant. All right, next up, I'd like to welcome Andrew Wilcox from Unilever.
Hi, everyone. Thanks so much, Tanya. It's great to be back for Geo for Good 2020. My name is Andrew Wilcox. I work in the sustainable sourcing team in Unilever's supply chain. I focus on the digital tools that help Unilever to accomplish our commitments to end deforestation and to protect and regenerate nature. As you can imagine, much of this work revolves around new opportunities in Earth observation. I'll be giving a bit of a different lightning talk today. Rather than focus on research that our team does with remote sensing, I'll be focusing on how Unilever is using Earth Engine and Google Cloud to work with partners with diverse backgrounds in geospatial data. This is what we believe unlocks the fullest potential of all things geo and drives positive change in the supply chain. Next slide, please. So my first point here is simple. The planet is complex. The convergence of sensor hardware, cloud infrastructure, and data science provides hope that we can make sense of what is happening to the world at planetary scale and before it's too late. But you're all here, so you all know what Earth Engine is capable of. So let's dive into some of the work we are doing to understand this complex world. Next slide. So here we're looking at most of Southeast Asia and showing what we believe are the best available data on current natural forest cover in green and oil palm plantations in blue. These are the foundational data that Unilever needs to achieve a deforestation-free supply chain by 2023. So let's take a closer look. Next slide. Here, we're zoomed into a region in West Borneo. To produce these data, we worked with a partner to create thousands of annotated image chips and ground truth points in order to deploy deep neural networks to classify natural forests and palm plantations, even in the most complex land use mosaics like this one. This snapshot helps us to start to untangle the complexity of these landscapes, but now we actually need to enrich the data to start to make sense of it all. So next slide. So here we're starting with the forests, and we're in the north of Sumatra, and we're adding another dimension to the forest cover data. This is where we've been working with the partner to integrate available LiDAR data to model tree canopy height in order to better understand forests and the supply chain. The color ramp here indicating tall forests in hot colors and short forests in cool colors. So next slide. Now we're going from the forests to seeing how we're enriching the palm data, focusing not on the height of the trees, but on how the crop is changing through time. Here we're visualizing the 3 previous years in a 3-band image. So the way to read it is that the image is white where palm has been present in all 3 years, blue where the crop was replanted 3 years prior, and yellow and reds are where the crop has matured 2 years and 1 year previously. Since the palm data are multi-temporal, they help us to see where the planting of the crop is accelerating and to take appropriate action when this is close to forests and other ecosystems. Next slide. So this brings me to my second key point, that on top of the complexity of planetary processes lies the scale of the modern supply chain, including tens of thousands of factories, millions of farmers, and millions of hectares of land. With a diverse portfolio of brands, Unilever is a significant buyer of many agricultural raw materials with a supply chain that truly spans the world. Here we're seeing palm oil mills in Southeast Asia as pink dots overlaid on the forest and the palm data layers we just saw. Next slide. And here we've gone from merely observing the locations of mills to using Earth Engine's algorithms to actually model the sourcing catchments of the mills and segment them into discrete regions. We worked with the data set that combines Google Maps road data with OpenStreetMap road data into a global friction surface. This allows us to bring new levels of transparency by more accurately capturing sourcing patterns based on actual transportation infrastructure, with each colored block here corresponding to a single mill. Next slide. And now you see this same concept at a much higher resolution view focused on an individual mill surrounded by other mills. The graphic compares the modeled mill catchment with the conventional approach, which is to draw a 50-kilometer radius around each mill. You can clearly see areas with stronger and weaker links to the mill in the center, with the strongest links in purple and the weakest links in black. And it's this visibility of the supply chain that enables action based on the data about the complex planet. So last slide, we see how we're bringing it all together. And as I said at the beginning, we're not going to be your usual lightning talk. And I hope this really gives a sense of the system that Unilever is striving to be a part of by use of Earth Engine and participating in communities like Geo for Good. So thanks everyone for your time, and I'm really looking forward to continuing on this journey.
Thanks, Andrew. Let's all give him a good round of applause. Next up, we've got Muriel Arantes from Ecam.
Thank you, Tanya. Hi, everyone. I'm a geographer with Ecam, a NGO formed by a Brazilian team that works for the conservation of the Amazon since 2002. I'm glad to be here sharing experience and hopefully offering geotechnology support to the most vulnerable. Next, please. And from our experience at Ecam, we know that traditional communities such as indigenous people and Quilombola are among the most vulnerable in general. So you can imagine the situation during the pandemic of COVID-19. Next, please. Ecam received a request for help from several Brazilian states, and in response, we were present in 23 municipalities providing basic food and hygiene kits. However, this is not enough. We need a strategy to deal with COVID-19 arriving at the villages, medium and long term. And given this context, next, please. Given this context, we mapped the vulnerability of traditional communities in the Amazon face COVID-19. This map is based on 17 indicators that go beyond the isolated numbers, like numbers of death or contamination, for example. We work with data from food safety, communication, demography, and others. Next, please. Our teams of field work and geoprocessing concentrated the efforts to collect and process the data from the communities in order to identify vulnerable areas in their territories. And most important, understand what makes them vulnerable the most. Next, please. We look at this data into the following points: origin, location, and extension. The method that allowed us to do this kind of approach is the multi-criteria analysis. Next, please. We followed 6 technical steps, is detailed in this link below if you want to know more. But basically, we worked in 3 moments. First, we had input data from the communities, and then our teams worked with the correlation between indicators. And finally, we did some adjustments validating all the process, because this was a work made by many hands. Next, please. The maps resulting from this work have this following background: basic data such as location, and correlated data grouped by theme and represented in the source as indigenous villages, for example. Next, please. We worked with 7 Quilombola territories and 3 indigenous land. Next, please. For indigenous communities, we had 15 indicators and 17 to Quilombola communities. We had data that coming from their indigenous organizations, and because of that are represented by village group. We also had data coming from the municipality represented by their boundaries. But the most important to analyze these indicators is to keep the correlation between them, and at the same time, keep the level of importance to each one. For example, one of the greatest weights was given to the percentage of people over 60 years old, because this is more risky in this case. Next, please. The results on the maps are shown in different levels of vulnerability for each communities, and this is already published in the MyMaps platform, so everybody can access, including the decision makers, so they can use this information to optimize their resources, helping those who need it the most. Next, please. The greatest lesson we learned from this work is that the support to face COVID-19 may not be only linked to healthcare. In some cases, having a smartphone with internet, for example, can greatly decrease the circulation of people and promoting access to important data. And therefore, we expect to be able to bring this mapping to more communities and helping give more visibility to their situation, their necessities. Next, please. Thank you very much for listening to me. I'll be happy to answer any questions about this work. Please feel free to send me an email.
Thank you very much, Muriel, and thank you, Ecam. Next up, I'd like to welcome Aaron Doucette from Applied Geographics.
Hi, everyone. I'm Aaron with AppGeo, and today I'll be sharing the story behind Bring Food. Next slide, please. And Bring Food is the route planning app transforming food accessibility. Next. I wanted to start off with a quick introduction to AppGeo. We're a geospatial consulting firm and Google Maps partner based in Boston, but with employees all throughout the US. And part of what I believe makes us unique is our commitment to shared value, collaboration, and open source tech. Next. So Greater Boston was one of the first big hotspots for COVID-19 in the US, and we saw a dramatic impact on our surrounding communities. Our company president, Rich Grady, wanted to find a way that we could help. And one issue that quickly rose to the surface in terms of both severity and immediacy was food insecurity. Simply put, lack of consistent access to enough food for an active, healthy life. Next slide, please. The situation worsened as those populations already most vulnerable to food insecurity, as you can see on this graph, were the same segments facing massive layoffs, furloughs, and loss of jobs in reaction to the pandemic and resulting shutdowns. Food pantries were among the organizations on the front lines of helping people now in dire need of food. However, this unprecedented rise in demand, coupled with social distancing guidelines, created yet another problem. Next, please. Many factors led to people not being able to come in person to get their groceries, as you can imagine. For one, food pantries wanted to limit the need for their patrons to travel to their site and have to wait in lines or potentially crowded spaces. Additionally, if someone was sick, we don't want to put others at risk by having them leave their home. Next, please. It was this very problem that led to the creation of Bring Food, AppGeo's response to what we saw going on in the very communities our staff live and work in. By starting and from a point of understanding exactly what the situation was on the ground at our partner organizations and designing an application to fit those exact needs, the Bring Food initiative came to life. Next, please. So our partner organizations needed to quickly move to a delivery model. So in response to this need, we created a completely free multi-vehicle routing tool that is super easy and accessible to use. This helped several organizations rapidly switch to delivery for 100% of their customers. This massively freed up volunteer resources to focus on the deliveries rather than the planning, which was a major bottleneck in the process. Next. So how does it all work? Given a spreadsheet of addresses, we calculate the optimal way for a certain number of vehicles to reach all of them. We geocode, cluster, then route. We also built in some features which help adapt the routing to the specific constraints of a given organization. Next. So I'm going to really quickly walk you through the process of how the app works, starting with the simple process of uploading a spreadsheet. And we designed this to have lots of flexibility in how this input data is formatted. Next. Before the routing begins, we parse the list and give the opportunity to correct any addresses that may have been entered incorrectly or geocoded incorrectly. This quickly allows potential problems to be identified and fixed early, especially since we might be relying on user-submitted data. Next. Once we've got our points, AppGeo's clustering algorithm assigns a vehicle to a set of homes, and Google Maps APIs provide the most efficient routing between them all. Next. The user can also visually inspect all the stops along a given route, or even hop into Street View for verification of what the home is going to look like. You can also rerun the optimization as many times as you need to, should your delivery parameters change day to day. Next. I do want to share this customer feedback with you from one of our very first users. Using Bring Food, what used to take us hours is now done in under 5 minutes. And we believe by helping these organizations save valuable time, we're able to multiply the impact of their volunteers and help them switch to a delivery model much more seamlessly with limited resources. Next. Here you can see how the program has grown since we launched just back in July. All of this wouldn't be possible without Google's support, providing credits for geocoding and the like to help keep the application free for all these communities in need throughout the US. Next. So just wrapping up now, on behalf of AppGeo, thank you again for having us present here. I encourage you to check out our website, bringfood.care. And if there are communities in your local area that you think could benefit from this application, feel free to forward it along, and we look forward to signing them up. And thank you again.
Really inspiring work, Aaron. Thank you so much. Let's have a round of applause for Aaron. Our final speaker today is TC from Yale University. Take it away, TC.
Thanks, Tanya, and thanks, Google, for having me here. I'm TC. I'm a PhD candidate at Yale University, and I work on climate science. And one of the things I'm interested in is urbanization and how it affects local climate. Next slide, please. So one thing I work on is the urban heat island effect. And the idea is that cities, due to the way they change the surface, surface structure, actually increases the temperature at the local scale. And this, of course, leads to higher heat stress, more energy use, and more secondary air pollution in cities. Next slide, please. So one issue with kind of trying to get a consistent understanding of the urban heat island is you need to define both an urban area and a rural reference against which you can see that temperature differential. And this is hard to do. For instance, for administrative boundaries, they are not the same as the physical boundaries of cities or the places where the land cover has actually changed. You can see an example here for Beijing and Tokyo, where for Beijing, the area around the city is forested or croplands, but for Tokyo, it's basically a concrete jungle. Next slide, please. So a couple of years ago, I developed a methodology to create a consistent urban heat island characterization for the whole globe. And the data set is now actually in the Earth Engine data catalog. And you can use the QR code to go to the web app and explore the data and download it. And you can also get more information about the app itself and the data set from that link below. Next slide, please. So I did this for the entire globe and for like cluster means, so urban cluster means. So the next thing I was interested in is looking at how that urban heat island varied between the city. So we basically got a random sample of cities at the whole global scale, like roughly 30 cities. And we kind of found out like how much urban heat island intensity was for different income groups. And what we found was in 72% of the city we considered, the surface urban heat island intensity was actually higher for poorer neighborhoods. Next slide, please. However, this particular study was done with a random sample, which kind of combined the socioeconomic uniqueness of different countries. So the next thing we tried was to try to recreate this study, but for the US. So we basically created a new, like a modified methodology to try to kind of compensate for the difference between physical boundaries and administrative boundaries But doing so, we were able to create an urban heat island database for all census tracts which were urban in the US. And you can see the urban heat island intensity on the map on the screen here. Next slide, please. So we found that for the US, for instance, in over 90% of the 497 urbanized areas we considered, the urban heat island intensity was actually higher for census tracts with lower percentage of white populations, which means that in general in cities, minority populations are being exposed to higher urban heat island intensity. And this is also true for poorer people who are being exposed to higher UHI intensity. And this means that it is important to know not only what the urban heat island intensity is, but also where it is and how it may affect potentially vulnerable populations. Next slide, please. And we created another app to kind of display this disparity in urban heat islands. And you can see a screenshot of the app here, and there's a QR code which you can use to explore the data. But basically, you can compare the urban heat island intensity at the census tract level, and also the demographic information from the U.S. Census Bureau. Next slide, please. So currently, I am also trying to look at how this is affected. This urban heat island intensity is affected by urban growth. As you can see from the animations here, urban areas have been growing at a rapid pace over the last couple of decades. And the idea is using Google Earth Engine, I'm basically finding a way to understand the dynamics of both urban areas and their rural references, and using that to characterize the long-term trends in urban heat islands. Next slide, please. So I would like to thank Google once again for this opportunity, and for Google Earth Engine for being a huge help for doing this kind of analysis at the global scale. And hopefully, like with this data set, we can better allocate resources as we move towards a warmer and basically more urbanized world.
Thank you very much, TC. And thank you to all of our speakers. That was a whirlwind tour of really inspiring stories around the world. I really appreciate you sharing your work with us, and I hope the rest of the summit participants do too. Have a great summit, everybody. Bye.
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 Thanks.